now let's start with the technical stuff. I have split the talk in two parts. The first part is well, I don't know, it depends of your background, but it's probably the boring part. It's the part about the algorithm, which is the specialized interval algorithm we implemented in that solver. And the second part it's about applications. Which applications we have been able to feasibly solve with this particular algorithm. So probably we'll go quickly through the first part and we'll focus on the second part. Okay, but you have some questions, you can interrupt me, you can ask me, so whatever. So let's start with the first part. Well, interpret methods. Interpret methods are very good algorithms, and they are usually applied when you have huge problems. When you may have huge problems. Usually you have huge problems in optimization when you have this kind of situation. We have problems that involve different blocks of variables. And blocks usually come from different periods or different commodities or different whatever. When you have this kind of problems with different blocks, usually you have a large number of variables and a large number of constraints. In my case, I will focus on the problems with linking constraints. You have a lot of blocks for different variables, and you have linking constraints that link all the different blocks. These are very common modeling tool in different applications, as in logistics, telecommunications, big data, data science, whatever. And all these problems have in common one thing: they are huge or very large. Okay. Okay. So, well, interpret methods, the standard interpret methods, for instance, in Cplex, the barrier method, it's already a good tool for this kind of problem. So then the question is, if IPM's interpret methods are so good for these large problems, why do we need to look for specialized interpret methods? The question is that all these commercial solvers like Cplex, Robi, Express, Mosaic, not Glob yet, Glob has no interpret method, okay? They rely on Cholesky factorization. So when they are at that point, they want to compute the next movement direction, they need to solve a system of equations using Cholesky factorization. That's fine for most problems, but when you have a million or billion of constraints or variables, you cannot use Cholesky. It's too difficult. You need too much memory. And then in that case, it's very important to use an alternative solution method, for instance, conjugate gradients. So most specialized interpret methods use conjugate gradients for solving the direction of movement. And that's a method that I'm going to explain now, okay? We have developed this method in several papers. We started in 2000, well, not working continuously, but we have different papers of this approach. We recently implemented in that solver, and I'm going now to explain a little bit how this method and this solver works, but very quickly. Okay, so which is the kind of problem we want to solve? We want to solve this kind of problems. So we have k different blocks of variables, okay? And the blue part are the block constraints for each block. So for variables x1, we have to satisfy this constraint, n1, x1 equal to v1, and exactly the same for the rest, nk, xa equal to vk. So these are the block constraints, okay? And the objective function, it's a sum of functions for each block, okay? F can be linear, quadratic, convex. The important thing is that it's convex, and also it has to be separable. That means that the Hessian of these functions has to be diagonal. That's the only requirement for the efficiency of the method, okay? So if we only had the blue part, this problem will be separable in k smaller problems. But that's not the case. In most applications, we usually have this red part, which are the linking constraints. The linking constraints mean that L1 times x1 plus L2 times x2 until Lk plus xa has to be equal to some total capacity or whatever, okay? So this linking constraint made the problem difficult. It's exactly the same as if you try to solve a diagonal system of equations. It's very easy. But if you add some constraint, some equation linking all the variables, then the system is no longer trivial, okay? So 2 questions. Yes.
So in the linking constraint, is that an I, meaning identity matrix?
That one. Oh, these are slacks. These are
for the slacks.
This is a measure of a slack, just in case you have something which is not equal to something, but less or equal. This is just a slack part.
And if we said separable again, was that just separable across the blocks, or does it need to be separable across the variables in the blocks for the objective function?
For all the blocks and all the variables. So okay. The Hessians for each block has to be diagonal. Okay, that's the only requirement. Okay, or if you consider a quadratic term, if its function is quadratic, then the Q matrix of the quadratic term has to be diagonal. Okay? That's the only requirement. Okay. Well, if it's not diagonal, the mathematics behind that work, but then the method is no longer efficient. Okay, that's the only. Okay, so if you try to solve this kind of problems using simplex-like methods, you have density loss decomposition or cutting planes. In interval methods, you have some other choice, which is the algorithm I'm going to explain very quickly. So, well, I have no time to explain how IPM's interval methods work, but basically the idea is, given any problem, any convex problem, you can formulate the KKT system, the Karush-Kantaker conditions. If you solve that system, you solve the problem. Okay, that is the KKT system. The KKT conditions have three parts. First part is dual feasibility. Second part is primal feasibility, and the last part is the complementarity. Interval methods perturb the complementarity. Here, in the original KKT system, here we have a 0. We perturb that by mu, and then we solve for each mu a solution of that. Okay, and then we tend mu to 0. If we do that, we obtain a path of points that converge to the optimal solution, which is named the central path. That's the central path. Interval methods follow approximately the central path. Okay, they do something like starting from x0, go to x1, x2 until that. That's why these methods are named path following methods, because they follow in an approximate way the central path. Well, I'm not going to explain that in detail, but that's the idea. Anyway, from my computational point of view, what's the difficult part? The difficult part is that to move from x0 to x1 to x2, we have to solve a system of equations to obtain the direction of movement. That's the only interesting part for this talk, okay? So the system of equation, it's that. We have to solve a system with matrix that involves matrix A times A transpose and scale it by something that it's a diagonal. Zeta, it's a scaling matrix. It's not important, it's not relevant for this talk. Zeta is something that depends on the values of the variables at the current iteration. That's all, okay? And what's A? A is just the constraints matrix of the problem. A has this structure. So we have to solve a system with A, some diagonal scaling matrix, A transpose. That's all. So in Bollock angular structures, what's the structure of this system, A zeta transpose? Is that A zeta transpose, this is our A matrix, the block angular matrix. Zeta, we can break zeta according to the different blocks. The system A zeta transpose has this form. So we have four different parts, 4 different submatrices. This submatrix, it's made by Ni times zeta I times Ni transpose. We have K of these blocks. This part involves the cross product between N's and L's. This is the transpose of that. And finally, the last part is the one related with the linking constraints. Li times zeta times Li transpose, sum for all the blocks, plus zeta 0 is the one related to the identity, the slags variables mentioned by David before, okay? That's all. So this is our system. We have to solve something with this matrix that has 4 submatrices, B, C, C transpose D. So you consider now our system, and you consider the same partitioning for the variables on the right-hand side, okay? And you apply a Gaussian elimination. This system is equivalent to that one, okay? That's just applying one step of Gaussian elimination at matrix level. That's all. So systems with B, these are trivial. Why? Because B, it's a block matrix. It's a block diagonal matrix. So you can apply Cholesky factorization for these small parts. What about the second part? This is the sure complement of the system. This part, D minus C transpose B minus 1C, this part, in general, cannot be computed. It's too difficult by 2 reasons. First reason, you need the inverse of B. That's difficult, or you have to solve a lot of systems with C. The second reason, the system is usually dense, completely dense. So you have a lot of linking constraints. The system is dense, so you probably will consume all the memory of the computer. So our approach is use Cholesky for B, but use conjugate gradients for this part. Yes.
What's the dimension of that sure complement? Is that the number?
The number of linking constraints. It's that, the number of linking constraints. You have 1,000 linking constraints, the dimension of the short-complement is 1,000 times 1,000. You have 1 million by 1 million. So, but you have 1,000, even if you have 1,000, you have to compute that short-complement, you need to solve that, b minus 1 times c. So that means either, or you have the inverse of b, that's very time-consuming, or you need to solve a lot of system of equations to get this part. So in any case, it's not in general a good idea to compute the short component in general, okay? So the idea is use Cholesky for B, use conjugate gradients for this part. That's all, okay? But in general, when you want to apply conjugate gradient, you need a good preconditioner. That's something which is well known. If you try to apply a plain conjugate gradient method for that, the number of iterations you will perform will be very, very large. So you need a preconditioner. So the good point is that there is a very good preconditioner for this particular short complement. And I'm not going to enter into details, but there is a closed form expression of the inverse of the short complement. The inverse of the short complement is the Brush preconditioner. You multiply the system by the inverse, then you get an identity. The system then becomes trivial. So it can be proved, I'm not going to enter into details, but it can be proved, we prove in these papers that the inverse of that short complement, it's an infinite power series given by this term. This power series is convergent because the spectral radius of this matrix to the power of I is less than 1. Is less than 1. So imagine these are scalars. If these are scalars, you have a scalar which is less than 1, and you raise it to the power of I, and I goes to infinity. This term goes to 0. Okay, so that's exactly the same idea, but we are considering spectral radius of matrices, not the scalars. Okay, so that's it. Yeah. So which is a good preconditioner? So consider some terms of this infinite power series, that's all. So if you consider only one term of the infinite power series, the inverse of the system we want to solve, the precondition will be d minus 1, only this term. You consider two terms, we'll have something like that. The more terms you consider, the better is the preconditioner, but it's more expensive because you're taking more of these terms. And for each of these terms, you need to perform a matrix, you have to solve a system of equations, okay? So that's the idea. Okay. In general, the further the spectral radius is from 1, the better. Let's consider that the spectral radius is 0.1. If it's 0.1, when you raise to 0.1, you get 0.01. You raise to 3, you get a very small number. So considering only the first terms of this series, you get a very good approximation of the inverse. So in general, when the spectral radius is far from 1, you get a better preconditioner. But that's problem dependent. In some problems, the spectral radius is naturally far from 1, then this method is very efficient. When it's very close to 1, then the method is not so good, okay? I will only show you one result with propositions. We have several propositions about this method. I will skip them, but only want to show you that. The good point is that the spectral radius, well, because the spectral radius becomes smaller when you add quadratic terms to the objective function, it can be proved that the conjugate gradient is more efficient for quadratic or nonlinear problems when you have a Hessian than for linear problems. So this method is faster when you have quadratic or nonlinear convex problems than when you have linear problems, okay? In general, as a corollary of this result, it can be seen that the method is very efficient if the Hessian is large. So if the Hessian of the objective function goes to infinity, the spectral radius goes to 0. And then you have the best preconditioner. So that means that you solve the system of equations in nothing, in only one iteration. It's very fast. These are some results with one of the applications I will show you later, okay? This is a data confidentiality problem. It's a problem with 10 million variables, this number of constraints. And this is a pure quadratic problem, no linear term. So the objective function is only this, x transpose qx. And here I'm considering that q, the quadratic term, it's beta times identity. Beta is a scalar. And these are results for different betas. So the largest the beta, the better according to that result, because the Hessian goes to infinity, okay? So some results. These are some, well, these are results comparing our method with simplex. Okay, this is the number of iterations of the interior method for simplex and in our solver. It's very similar, but this is the CPU time. Look at the CPU time of simplex compared to the CPU time of that method. So when the problem is purely quadratic, that approach is very, very efficient. If you add a linear term, it's no longer so efficient. But well, in that case, the problem was purely quadratic. And we got exactly the same solution. I mean, we are not getting an approximate solution. No, we got exactly the same solution with a high precision, okay? So the idea is, if you have a pure quadratic problem and it's block-angular, this approach can be quite good, okay? Okay, finally, we have implemented this method, this algorithm in that solver. It's in C++. Well, for you, maybe this is not a huge number. For me, it is, okay? That's for me a lot of lines of code, okay? We have several options. We implemented it considering different predefined types of matrices because, well, we have to work with matrices, different types of matrices. We have general matrices, oriented and non-oriented network matrices, identity, diagonals, whatever. We have a parallel version. It was quite good. Using OpenNP, okay, it was very well because we have different blocks. So, well, and now I'm going to go to the second part. Okay, let's talk about different applications where we have applied this solver and we got quite good results. First application, it's a routing problem. It's a routing problem in telecommunications network. It's named the minimum congestion problem. The problem is the following. Okay, problem is the following. So consider you have a graph, a network, and you want to send several commodities from some origins to some destinations. Okay, that's the problem. It's a multi-commodity flow problem. Okay, but in that case, it's non-oriented. I mean, for every area we have flows, forward and backward flows. Okay, we have the x plus and the x minus. Okay. These are the network equation constraints. These are the flow conservation constraints for each block. K is the number of blocks. In a standard multi-commodity flow problem, we want to route problems at minimum cost. But in that case, that problem is infeasible. I mean, U is the capacity of the R's. And we have that, we add the total flows, and we force the total flows to be less or equal than the capacity, that problem is infeasible. So this is an infeasible multi-commodity flow problem. So the purpose of the minimum congestion problem is to increase the capacity of the R's to guarantee that the problem becomes feasible. And so we, for this purpose, we multiply the capacities by Y. Y is a scalar associated to each R. J, it's indexed over the number of arcs, okay? So we multiply each capacity, the capacity of each R by Yj, and we want to minimize the infinite norm of Y. That is, we want to minimize the maximum of the increments, okay? So how to do that in optimization? The usual thing is we minimize Z, artificial variable, and Z has to be greater or equal than Yj for every R. That's all. So with that formulation, that's the formulation of the minimum congestion problem. That formulation is not a very good formulation for integral methods. Why? Because this variable Z appears in a lot of constraints. So you will have a dense column basically. That usually creates a lot of difficulties to interpret methods. Dense columns are problematic because of this A times A transpose system of equations. So, for instance, we do that. Our preconditioner will be something like that. We'll have a dense window in the preconditioner. That's a bad idea. So what's a better idea? Consider our formulation. We will consider a different Z for each R. That is the auxiliary variable to compute the maximum norm. So if we consider a different set for each variable, we minimize the set of the first R. We impose that set J is greater or equal than this scalar, okay? This increment, and then we force that Cj is equal to Cj plus 1. That's equivalent to the first formulation. Now we have more constraints. The matrix D, the preconditioner, is larger, but the number of non-zero it's very small. It's much smaller. So that's a much better formulation. And that's the one we use. And this is a block angular problem with quite a lot of linking constraints, but the structure of the linking constraints is very simple, okay? So some results. This problem is known to be difficult for simplex methods. So for instance, simplex has some problems solving this kind of models. These are results solving some instances in the literature. These are the name of the instances. This is the number of blocks, the number of commodities, the number of constraints, the number of variables. These are not very large problems, but they are quite difficult. This minimum congestion problem is known to be difficult for commercial solvers like simplex, okay? And these are results using simplex and using block IP, our solver. So for the largest instances, you see that this approach, it's about 10 times faster than simplex, which is a good result. Beating simplex is difficult. I mean, especially if you are a single researcher, they are a company. I'm a one. So I mean, that for me, that are very good results. Okay. Okay. So that's the first application. Let's go to the second application. The second application, it's a field where I have been working in the last 10 years quite actively. It's a problem of data confidentiality when you publish statistical tables. I did some work with Eurostat, the statistical agency of the European Commission, and they have a lot of these problems. The problem is the following, okay? The problem is, well, national statistical institutes have to publish data about people, okay? So the problem is that when they publish a table of data, for instance, a table of data could be considered the census of Europe, or United States also apply these techniques, okay? They produce a table crossing, for instance, information about number of people by country and by profession. That's a two-dimensional table. So you generate a table, counties, profession, or cities, profession, and you give the number of people in this Cartesian product. Okay, so if you produce another table where you provide the average salary of the people, if in some country there is only one person with a profession, you are automatically giving the salary to that person. So you have to do something with that. One of the techniques is to perturb numbers, to perturb the data. And that's this approach. This approach is named controlled tabular adjustment. It's a perturbation method. So the idea is, consider a table. You perturb some numbers, you change some numbers, okay, to hide information of some individuals. But of course, if you change some numbers, then in a table, the sum by rows and the sum by columns have to be equal to the marginal. If you change something, you have to readjust the other numbers to preserve the totals. That's the idea, that's the method. So a table, a statistical table, is just a vector of cells that satisfies some linear equations. The linear equations mean that sum by rows, sum by columns equal to the marginals. So if you perturb something, that means that you are adding some x, a perturbation vector, and you want that x plus a, the original data, the original numbers plus the perturbation, multiplied by a, which are the linear equation of the table, this has to be equal to the marginal values. So the idea is, which is the vector of minimum perturbations, which is the vector of minimum perturbation according to some distance, to some either Euclidean or Manhattan distance, okay, such that Ax is equal to 0. That means we guarantee the marginals, and x is with some values. That's the problem, basically. So that's a very general problem. You can apply that to any table. So the question is, well, what that has to do with block angular problems? The idea is that a particular class of tables is block angular. For instance, three-dimensional tables. Let's suppose that you don't cross two variables, you cross three variables. You have a census of a country, and you cross by profession, county, and sex or gender. Okay. So now this table is for males. This table is for females. It's a slice. It's a two-dimensional table. But if you consider by the third variable, then you have another set of constraints. So basically, that's a cube of information. It's a cube of data. You can think it's a kind of tensor. Okay, it's a cube of data. Okay, so For males, you have one block of equations. For females, you have a second block of equations. And you have one last block, which are the linking constraints. That implies that the sum of this number by this number has to be equal to this number. So this A3D table is just very similar. It's exactly the same as a multi-commodity flow problem. It has the same structure. It's the same of a tensor. I think that these methods can be applied to tensor problems. I don't know, still hope, but a formulation of a tensor problem is exactly that. Okay? So then the idea is try to solve this kind of problems using our solver. And these are the results. Well, we have results using L1 as a distance, the Manhattan distance, or L2. In that case, we have a linear problem. We have to split each variable in two parts, the positive and the negative. That's the standard thing. And here we have a quadratic problem. Okay? So let's start with the results for L1. For L1 distance, okay, for the linear problems. So these are problems where these are the number of categories of the three variables we are crossing. The largest problems have 500, let's say, professors, 50 counties, let's say. Well, 500 genders is difficult, but well, let's suppose, okay, well, we are crossing variables with this number of categories. So this is the number of constraints. This is the number of variables. You see that here we have 250 million, so these are quite large problems, okay? And this is the number, the CPU time with our solver or with Simplex. Well, you see, the results are so there is a big gain by using conjugate gradients in combination with Cholesky, okay? The results for the L2 distance, for the Euclidean distance, are even better. Why? Because I told you, quadratic problems are better for conjugate gradients. And these are the results. The size of distance is the same, okay? And you see, this problem with 100 millions of variables, and this number of constants, was solved in 28 seconds, okay? I'm not using a supercomputer. It's a server, but it's not a huge machine. This is the number of seconds needed by Simplex. Why? Because Simplex uses Cholesky factorizations. We are using Cholesky and conjugate gradients, okay? Okay. I have time. Well, if I run out of time, I will skip some of the applications, but I think, okay. Let's go for the third application. The third and the fourth are still work in progress. It's something we are, it's still not finished, but we have already get some good results. The third application, it's a problem for machine learning. But probably you are more familiar than I. I'm not an expert in machine learning or in support vector machines, but we have started to apply this method to support vector machines. Let me explain. Are you familiar with support vector machines? Yes, all of you? So I can skip some. Yes. Okay, so that's a support vector machine, okay? Probably you know, support vector machine, you have two types of, you have data, you have a matrix of points, and these points belong to two classes, okay? You have the triangles or the circles. And you want to compute a hyperplane separating these two classes. And the idea is, well, you want parallel hyperplanes without wide merging. That's the idea. That's a bad class. This will be a bad classification because this triangle, it's well classified, but it's too close to the second class. This is not happening here. We have this is named the margin of the two hyperplanes. Okay? Well, so which is the data we need to solve that problem? We need the matrix of points, okay, n points, and features. Features is the number of attributes for each point, okay? And we need also a diagonal matrix that tell us, a diagonal matrix where the diagonal terms tell us whether the point I belongs to class +1 or -1. So triangles are +1, circles are -1. That's the idea of a support vector machine. I'm not going to enter into this, but if you want to solve that problem, you have to solve either this primal formulation or this dual formulation. That's the primal formulation of the support vector machine. Which are the optimization variables in support vector machines? W is the normal vector of the hyperplane, and gamma is the intercept of the independent term of the hyperplane. That's all. Okay? And what do we want to do? We want to minimize this term, this quadratic term is the normal vector, is the Euclidean normal vector. Basically, minimizing that, it's equivalent to maximizing the separation margin. Well, I'm not going to enter into details, okay? Plus this term, what's this term? This new is a parameter to combine these two terms, and this term is the sum of some select variables. These slugs account for the misclassification. Basically, we want that the circles belong to the class +1 and the triangles to the other one. But we have some misclassification errors. These misclassification errors are given by these slide variables. So we want to reduce the misclassification errors. These are opposite objectives. The wider the margin, the more misclassification error we'll have. So we combine these two opposite objectives by this new. These are prefixed parameters. Okay, so that's all. So that's the primal formulation. It's not difficult to see that you can. This is a quadratic optimization problem. You compute the dual of that, you get that. Again, I can have no time to develop that. Okay, so but either if you solve that, the primal formulation, the dual formulation. The problem with, if you try to solve that with integral methods, is that you will have to solve systems with A transpose. Here you have A transpose in the objective function of the dual, or if you solve using that, you will have to solve a system of equations with A times zeta times A transpose. So in both cases, you have to solve systems with A transpose. And which is the size of A transpose? Is number of points. Remember that the size of A is a rectangle of number of points times features, attributes, okay? So A transpose can be a huge matrix of size number of points. And the rank of this matrix is the minimum of the number of points and the number of features. So it can be a large matrix, maybe with a low dimension rank, depending on the number of features. So up to now, all integral methods that have been applied to that technique were good when the number of attributes n was small. So when you have a problem like that, where the data, the matrix of data was something like that, so you have a lot of points, but very few features, so the matrix A transpose was a very low rank matrix, then integral methods were okay. There were some specialized methods that were developed to work well. But in general, this is not the case. In general, you have a lot of points, a lot of features. In that case, you cannot use integral methods. But there is a way to reformulate that problem to get a block angular structure. And the trick is the following. Consider that you have a lot of points, but you can split the matrix, you can partition the points in different blocks. So you have a partition of the data set in different blocks, okay? Each block has its own points, okay? So you will compute for each block a particular support vector machine. But then you have to impose that the support vector machine of block I has to be equal to the support vector machine of the next block. So that way you get automatically a block angular structure. So you have a constraint, a group of constraints for the support vector machine 1, the points of block 1, second block for the second group of points, third block of points until block K. And finally, you have some linking constraints that basically only say that the support vector machine of block 1 has to be equal to block 2 to block 3, and that's all. So this is a block angular reformulation of the support vector machine problem. What's the benefit? The benefit is that if you try to solve the original support vector machine, you have to deal with systems of with A transpose. The factorization of that has a cost of O n to 3. Okay? Now we have to solve K systems of size n divided by K. N divided by K because we have reduced the size of points. How many systems of that? K times. You have K blocks of that. So you do these operations, the cost of that is N3 divided by K2. So we have reduced a lot of the complexity. Well, which is the downside? The downside is that now you have linking constraints. So you need a good method to deal with the linking constraints. But that's exactly what our solver knows to do. Okay? So that's the idea.
I have a question.
Yes?
Is there any smart way of selecting the blocks? Or in the second related question, how would you select the number of such blocks?
To be honest, probably there is a better way, but up to now, you just consider the matrix, okay, the whole matrix of points, and because these blocks AI transpose are almost dense. In a support vector machine, the constraints is dense. we don't use a sparse Cholesky solver for this part. We use a dense Cholesky solver. That one is laid back. So we did some experiments and show that when you have a system of dimensions 600, layback it's quite efficient. When you go to 2000, for instance, layback starts to be much efficient. So basically, we consider that something around 500 or 1000, it's a good number of points. That's all. Probably there is a smarter way, but with that, the idea worked. So, okay.
Question. So if you do this linking, you can't use a generic kernel function, right? You can't use like a Gaussian kernel or things like that anymore.
No, I cannot. The question is if I can use. No, I can. This is just for linear kernels. Okay. No, that's another problem with that technique. This is only for linear kernels. For nonlinear kernels, the only way will be to, well,
you have to be able to deal with the dual.
Exactly, to be able to solve the dual, to solve that, or to, from that expression, you only have the kernel function, the kernel matrix, to perform some kind of Cholesky factorization a priori, and then say, this Cholesky factorization, it is the matrix that you are going to consider in the dual. That will be the idea.
So you're saying it could be a way to do it?
There is a way. Well, okay. In theory, you have the final kernel.
Yeah.
In theory, there are ways to compute, but these are a bit difficult. There are ways to compute the mapping function, that translates from the features to the new space. There are ways to compute that. For instance, doing a Cholesky factorization a priori. The problem is that maybe this Cholesky factorization it's for the kernel for the final kernel. So it can be more difficult to compute this Cholesky factorization than later to solve the support vector machine problem. So, well, some results. These are results with real. These are real support vector machines instances in the literature. These are. Well, you are familiar with support vector machines. You probably know these names. Okay. The first set are instances with few features. The last ones are instances where the number of features is large. This is the number of features. This is the number of points. And this is the number of blocks I use. You divide the number of points by the number of blocks, you will get something like 500, 1000, which is what I tried to explain before. Okay. So these are the sizes of the instance I'm considering here. Okay. And the next slide are results using the best interior point approaches I know for this kind of problems. Cplex is standard Cplex. It's a very good solver, so it can deal with them. This method, SVM OOPS, it's a method developed by Gonchi and Woodson in Edinburgh. It's probably the best interior point method for support vector machine problems. And this is the result we got with our approach. Well, this method is very good when you have a small number of features. When you have a lot of points, few features. So you look at the results for the first type of problems with few features. Our approach was never the best one. The best one is marked in blue, the worst one in red. So our approach was, in most cases, the worst one. Okay. But when you go to the instances where the number of features is large, okay, you see that this approach was not able to solve any instance. Okay. And Cplex was very time consuming. You see, this took this number. Well, our method, well, it was the best one. That said, probably you know that in the literature, there are much faster methods for support vector machines that are based on first order methods. Basically, they remove the constraints, they move the constraints to the objective function using a non-smooth function, and then they apply some first order method. They don't get the optimal solution. They don't get the same precision of these approaches, but they get something that it's okay, it's good. It's a good it classifies pretty well the points. Okay.
So there is this library leap SVM or something.
Leap SVM. So this approach is faster than leap. Block IP is faster than leap SVM. It's faster than leap SVM in these instances, but it's not faster than leap linear. Leap linear. It's the specialization of leap SVM when you have linear kernels. Leap linear, it's I mean, it's amazing. It can solve all these instances in less than 1 second.
And it's yeah, so like, and the precision is like, so it doesn't find the optimum solution, you're saying, or
Cool, live linear.
live linear?
Well, live linear, for instance, live linear cannot solve this formulation. Live linear does not use gamma. It only solves a problem with a hyperplane where you only have W, the normal vector, not the gamma. So you have to do a trick that lifts the problem to a higher space. You have n attributes, you have to lift the problem to a space of n plus 1, and the new attribute is the gamma. So you are not solving the same problem, you're solving a related problem.
Okay.
But, well, because anyway, you want to classify, you don't want the optimal solution, you want to classify points. So at the end, the solution obtained by linear is pretty good. But well, we are optimizers. I mean, as an optimizer, you have a problem, you want to solve that problem, not a related problem, you want to solve that problem. So that's a different approach. But if you want to solve that problem, that approach, it's very good. If you want to solve a related problem, linear is better. Okay.
So I do also have a curiosity
Sorry?
around this table. So you say that when the number of attributes is large compared to the number of points, your algorithm is outperforming the competitors. I was wondering whether you were running the primal version of the competitors or the dual version. Because the dual, of course, the guys in this situation, column cancel, etc., are much faster.
Yeah. I use the version that I didn't implement any model for this. I just input the data of the supervector machine. Right. So these guys use the dual version.
They use the dual.
They use the dual version. Yes, these guys use the dual version. They cannot solve the primal. They use the dual version.
All right.
Okay. I mean, when Simplex, I use the same formulation that I'm using here, but not for this. This is a specialized algorithm for supervector machine. So to this algorithm, I only provide the data of the supervector machine. I don't provide any optimization model. Yes.
So you provide Simplex with the block angular formulation?
I tried it both. I had it here the details because I didn't want to bother you with details, but I tried it both formulation with Simplex. I tried it. That formulation, that one, with only one block, I mean, solving the huge problem, I also, the formulation with the multiple blocks. So I tried both formulation with Simplex, and here I'm reporting the fastest one for Simplex. I don't remember, some of them are with the one block formulation, some with the k blocks formulation. I mean, I'm not cheating. I'm using the best result for Simplex. Okay, so, oops. One more application, last one, maybe last one, and I will finish. Well, the final one is a combinatorial optimization problem. Maybe it's interesting for you, but you can look at the slides, okay? Okay, anyway, the last one is how to solve convex flow problems in transportation problems in bipartite networks. Well, the problem is the following. This is it's a minimum convex cost flow problem in bipartite networks. So consider you have a graph and a bipartite graph. So you have two blocks of nodes. Let's say the supply nodes and the demand nodes. And you want to send something from the supplies to the demands, okay? So that's the problem. This is a generalization of the transportation problem. So you have, these are the, capital J is the set of demands, capital I is the set of supplies, and we want that the demand dj has to be satisfied, and we have to send something from the supply nodes, and the SI is the maximum supply that we can provide from supply nodes, okay? And we want to minimize some function in the arcs, okay? This can be a linear function, a quadratic, and non-linear. The only requirement is that the Hessian has to be diagonal, nothing else, okay? And we have some capacities in the flows. So these are generalizations of the transportation problem. So, well, you will say, but this is not a block angular problem. It's not, but it can be reformulated. Let's consider that blocks are associated to J, to the demands. If you do that, then we have this reformulation. The first block, what's the meaning? E, it's a vector of ones. That means that all the flows arriving to one, to demand one, have to be equal. The sum of flows arriving to demand one has to be equal to the demand one. The sum of flows arriving to demand node 2 has to be equal to the 2, and so on. And finally, which are the linking constraints? The linking constraints are all the flows leaving from the supplies have to be less or equal than the supplies. So that's a block angular formulation of this kind of transportation problem. And the objective function can be anything, linear, quadratic, convex. That's all, okay? Then you have this reformulation, you can apply our solver. Let me show some results. These are results for linear problems where the costs in the objective function are integer. Why that's important? Because we want to try with the best solvers as far as we know in the world. And the best solver we found for this kind of problem, it's Lemon. Probably you are familiar with Lemon. It's a solver that implements all these pseudo-polynomial time algorithms for network flows as capacity scaling, cost scaling, cycle canceling, network simplex, okay? And that solvers only work well when you have integer costs. So these are resolved for problems with several number of origin nodes, destination nodes. This is the total number of variables and constraints. The largest problem has 1,000 million, so 1 billion of arcs, and this number of constraints, 5 million constraints. These are problems with 1,000 of nodes, supply nodes, 1 million or destination nodes, okay? In blue,
what kind of structure do you have on these instances?
Are
they
random? They are random. I mean,
They're random.
this number of nodes, and it's a full graph. I mean, we have arcs for all the combinations, and the numbers are random. I mean, there is no particular sector in favor of any solver. Okay. Okay. So these are the results with block IP. These two columns mean two different algorithms to compute well. Newton, predictor, corrector. These are particularities of the interior point method, okay? It's not important. Simplex using the dual simplex, the standard barrier, and the self-dual formulation. These are two variants of the interior point method implementation in simplex, and these are the four pseudo-polynomial time algorithms in Lemon. Well, the third three are polynomial time. The last one is network simplex, which is not. Okay? Well, you can see the results. In blue, again, we had the best result, okay? The time limit was 5 hours in all the executions. And, well, you see, the largest, let's go to the largest instance. We were able to solve it in less than 1 hour. Simplex could not. I think it was not by 5 hours time limit. I think in some cases was by memory consumption. It exhausted the memory of the machine. Okay? And Lemon, these polynomial time algorithms were quite good, but we were able to get better results. We outperformed it. Okay. Well, very quickly. Next results using fractional cost. So the objective function now are real numbers. Now we can only use the network simplex of Lemon. You can see the results. They are also in favor of our solver. Okay. Okay. Simplex could not solve the last instance. I don't know why, because integer of fractional should not be an issue, but we needed more time for that. And finally, for quadratic problems, here we can only compare with simplex because Lemon network simplex is only for linear. You can see the results. Okay, and again, the times are better. Quadratic simplifies a lot the solution of the problem when you use an interior point method. But again, we were better than simplex. Okay, and I will stop here. Okay, we will stop here because the last is an application of it's a facility location. It's a combinatorial optimization, but it's a facility location using a vendor's decomposition, and the subproblems of vendor's decomposition are very similar to this transportation problem. So it's the same idea. Okay. Okay. So I want to skip that application. Okay. And finally, well, there are more applications. For instance, we are trying some routing problems in telecommunication networks, transportation problems in neural networks. We tried this application developed by David and Aaron some years ago, but we got some results, but simplex is better than us, and the method they developed is far better than us or simplex. So I think there is nothing we can do better here, okay? And probably there are more applications. So some probably with vocabulary structure. I don't know if this method can be given a try. And that's all. That's the conclusions. There is a web page where you can download. The code it can be get for free for academic purposes. And this is a list of papers about this method, and that's all. Sorry, I hope that the talk was not too boring. Okay.
So you had this discussion at the start about the preconditioners and basically showing you can do either basically the 0 term or the 1 term preconditioner. Which preconditioners are you using in these?
The 0 term. The 0.
Okay, just the inverse.
The simplest preconditioner. It's the simplest one. Only 1 term of all the series.
And do you have a sense of whether or not using random data for the instances was causing the preconditioner to look better, because at some level the preconditioner is correcting for how non-random your instances are?
It could happen. In general, common sense is that when you have a real application, things are worse than when you generate random numbers. That's true. That's true. But well, you have some real data, you can send it. So that's all I can say. So I mean, we were looking for transportation problems with billions of variables. There is not in the literature. There is nothing. So we have to generate our own generator. So that's for instance, for support vector machines, we got good results.
Mm-hmm. That's real data,
and these are real. I mean, we didn't generate them.
Right.
For the rest of applications, we have some random instances, but some are real. So, I mean, it's difficult to say.
Any other questions?
And also, the parallel version works pretty well. We tried the parallel version for support vector machines, reduce the time a lot. I mean, using 24 cores, the speed up is about 15. It's very good because, well, we solve basically Cholesky systems, block Cholesky systems. So, I mean, it's a coarse grain parallelization. We're not doing small things in each processor. We do a lot of work in each processor. For example, the speed ups were much better with this method than with simplex. Speed up with simplex with 24 processor was 6, for us was 15. So, I mean, you have a huge problem, a huge application, maybe running that in parallel. And believe me, I'm not an expert in parallel computing. I just took OpenMP, the library. I say, okay, I have this loop and this loop. Do that in parallel, nothing else. But well, I'm sending Cholesky factories of that. Well, that's the idea of parallel computing. No, you have to do big blocks of work, not the small ones.
So there was the step that was sort of the linking step. So you basically do all the Choleskys, and then you had that linking step. That you're doing sequential, or would that also be able to be parallelized because of its structure?
No,
That's way back to the start.
Sorry, I didn't understand.
We'll follow up offline.
Okay.
Go ahead.
So we do all the Cholesky, all Cholesky parallel. But all this Cholesky step is also needed for the conjugate gradient. But the iteration of the conjugate gradient, you have to do a matrix vector product. And this matrix vector product, you have to compute again all the Cholesky factorization.
Oh, okay.
No, not the factorization, the solution.
The results. Okay.
Okay, the results.
Okay, let's thank the speaker.